Today we're going to cover Chapter 4, Section 5, Indeterminate Forms and L'Hopital's Rule. Yes? Did 3 and 4 yesterday, last class. Yeah. Indeterminate forms. What do you think that means? Indeterminate. Basically, what it means is it cannot be determined. So what kind of functions exist that don't really exist? The formal definition is it's a number the form 0 divided by 0, infinity divided by infinity, infinity times 0, or infinity minus infinity. They look like real numbers. But their values cannot be determined or assigned. Determined in a way that is consistent with rules of addition and multiplication of real numbers. So for rational numbers, we have a numerator and a denominator. Where the numerator and denominators go to 0 or infinity. First, we're talking about limits. Here we're going to look at limits going to either 0 or infinity, or actually any value x that makes the numerator and denominator 0. For example, the limit as x approaches 0 of sine x over x. Remember what this equals? 1. But when we first started doing it, the first thing you do when you have a limit function is you take the limit and put it in place of x. The sine of 0 is 0 over 0. That's an indeterminate amount. So how can sine x over x equal 1? That's what the topic is for today. Because what exactly is 0 over 0? The rules of algebra say that any number over itself is 1, but also has a rule that you cannot divide by 0. 0 over 0 is undefined, doesn't exist. So in this equation, what we have to do is we have to use a method invented by Bernoulli, the same guy who did the laminar flow, the fluid dynamics. He invented this method called L'Hopital's rule. He took it. There was a guy another mathematician in France named Guillaume de L'Hopital, and he invented this method where you can take indeterminate functions and find their derivatives. Remember, a derivative is the limit as x approaches some value. That's what we did in chapter 2. So, what L'Hopital's rule says is this. We're going to do an example, and I'll write down the actual L'Hopital's rule. So we know that as long as the top and bottom of a rational equation equals 0 over 0 or infinity over infinity, we can use L'Hopital's rule. L'Hopital's rule says this. If we get 0 over 0, infinity over infinity, we can take the top and bottom. This is f of x, and this is g of x. Take the derivative of both of them. What's the derivative of sine x? Cosine x. What's the derivative of x? Now, if we put 0 in there, what do we get? Cosine of 0 over 1. Cosine of 0 is 1. So there we have our proof again that the sine x over x as x goes to 0 is 1. Using L'Hopital's rule. So that means in today's class, we have to look at all of these possibilities. 0 over 0, infinity over infinity, 0 times infinity, infinity minus infinity. We have to see how all this applies with all of these. So let's define L'Hopital's. L'Hopital's rule. Suppose, let me see what we have here. Yeah. F of A and G of A equals 0. For any A in the interval AB. It's an open interval. First derivative of G cannot equal 0. Why is that? It has to be continuous. F and G are both continuous functions because they're differentiable, but they have certain conditions that have to apply. At the limit values, Remember, we say that the limit as x approaches a of f of x over g of x. So as long as they're continuous and f of a equals g of a and they both equal 0, the limit as x approaches a of the first derivatives of f of x and g of x should exist or will exist. Assuming f of x and g of x are differentiable. Let's look at a bunch of examples. Okay, so first off, what is the condition to use L'Hopital's rule? It has to be differentiable, it has to be continuous functions, yes. But when you plug in the limit value, it has to be 0 over 0, infinity over infinity, or any of those 4 categories. We're going to look at the first ones are going to be 0 over 0. Example 1. The limit as x approaches 0 of 3x minus sine x over x. If we put in 0 in there, what do we get? 3 times 0 is 0. Sine of 0 is 0 over 0. So right now, this satisfies our condition. So using L'Hopital's rule, what do we get? What's the derivative of the numerator? Derivative of 3x is 3. Derivative of sine is cosine. Derivative of x is 1. Now we put in our limit point. 3 minus cosine of 0 over 1. 3 minus 1 is 2. That's the limit. Again, what does the limit give us? That's the slope of the tangent line to a curve at the given point when x equals 2. That's the rate of change of that curve at that point. So it is differentiable. In other words, the derivative that didn't exist earlier now exists. Yes? One more time? Yes. How would that look like? Okay, that's a good question. Let's see this. So this is the function 1 over x squared. As x goes to 0, limits go to infinity. L'Hopital's rule also works for one-sided limits. So what we're finding here is at any point you can find the rate of change, the slope of that curve at any point. So even, I mean, it can cross the other line, but we're going to look at this point here. Likewise, that point there. So all we're looking for is any single point along the curve. So at this one, since it's undefined at 0, we can take the limit as x approaches 0 from the left and from the right and get use L'Hopital's rule there. So that's the beautiful thing about L'Hopital's rule. It works on an overall continuous function, or even like a function of 1 over x squared, where you can take one-sided limits, and they both exist. That's a very good question. Thank you. Let's take another example. Limit as x approaches 0 of square root of 1 plus x minus 1 over x. This one. Did anybody do the test before they started? Good. So is it 0 over 0? Yeah, because always test that, because if it's not 0 over 0, L'Hopital's won't work. You'll have to use the quotient rule. So we plug it in there, we get 0 over 0. So let's take the derivative of the top as x approaches 0. Okay, the easy derivative of the bottom is going to be 1. The derivative of square root of 1 plus x equals 1 plus x to the power 1/2. The derivative is, bring it down, so the derivative of that is 1 over 2 square root of 1 plus x. Derivative of 1 is 0. So this becomes the limit as x approaches 0 of 1 over 1 plus x. Is it 0 over 0 anymore? No. So now we can go ahead and plug in 0. So we get 1 on top, 1 plus 0, square root of 1. Square root of 1 is 1, so our answer is 1/2. The rate of change at 0 is 1 over 2. Limit as x approaches 0, 1 plus x minus 1 minus x over 2 over x squared. First off, is it 0 over 0? Yes. So we take the derivative of the top. Well, the bottom is going to be easiest, so it's 2x. Derivative of square root of 1 plus x. The derivative of 1 is gone. The derivative of x over 2. Over 2. X over 2 is the same thing as 1/2 times x. The derivative of this function, derivative of x is 1, so it's just 1/2, the coefficient. Okay, now what do we do? Find the 2 on top, so we need radical 1 plus x over radical 1 plus x. limit as x approaches 0 of 1 minus radical 1 plus x over 2 radical 1 plus x over 2x. Well, what happens here if we go to 0? Still get 0 over 0. So we got to do it again. So if you want to, you could algebraically simplify this even further. We have the limit as x approaches 0 of the top fraction times the flip of the bottom radical 1 plus x over x radical plus x. We get 0 over 0 again. So now we take it again. Take L'Hopital's rule again. As long as you get 0 over 0, you take the derivatives over and over and over until you get one non-zero component. So we have to do the product rule. We have to fix this thing algebraically. Just plug x in there as 0. So it's square root of 1. So on top it's negative 1/2. This is 1, so it's 4. That goes to 0. So it's negative 1/2 over 4 over 1. Makes it negative 1/2. Negative 1 over 8. That's the value of the limit as x goes to 0. Yeah. Otherwise, we'd have to fix this thing algebraically, which we wouldn't get us anywhere because we get the same answer at the very end. That was differentiating it twice with L'Hopital's. Let's do it again. Example number. Limit as x approaches 0 of x minus sine x over x squared. So again, 0 minus 0 over 0, so it's 0 over 0. So we do L'Hopital's rule. As x approaches 0, the derivative of x is 1. The derivative of sine is cosine over 2x. Still 0 over 0. So L'Hopital's again. Derivative of 1 is 0. Derivative of cosine is negative sine. Derivative of 2x is x. I mean 2. Sine of 0 is 0 over 2. So it is 0. Should have put 3 there. Oops. Another example. Limit as x approaches 0 of 1 minus cosine x over x plus x squared. Plug in 0, it's 0 over 0, so we can use L'Hopital's. The derivative of 1 is 0. Derivative of cosine is negative sine. The top is sine. Derivative of x is 1. Derivative of x squared is 2x. Again, 0, 0 over 1. Is 0. You repeat L'Hopital's rule until you get a non-zero numerator or denominator. It only works in rationals. We're done, yeah. Once one of them is not 0, you're done. Because if the top one's 0, the answer is 0. If the bottom one's 0, then it's infinity. Because 0 goes to inside 1 infinite times. All right. One-sided limits. We talked about earlier. Limit as x goes to 0 of sine x over x squared. We can do this equation 2 ways. Let's look at taking it from the left side and from the right side. Because this graph itself will look similar to the Atari function because we have an x squared on the bottom. So it has asymptotic points. Let's look at this thing 2 different ways. The first way, since we're dealing about L'Hopital's rule, let's use L'Hopital's rule. Derivative of sine, cosine. The derivative of 2x, or x squared, is 2x. If we plug in 0 inside there, what do we get? Another way we could have done this, the function sine x over x squared, we could have split it up using the rules we learned in chapter 2. X squared can be x times 1 over x. And we could take the limit of both functions separately. Without needing to use L'Hopital's rule. What is the limit of sine x over x as x goes to 0? 1. We also just proved it not too long ago. So that's the first one. What's the limit as x goes to 0 of 1 over x? 1 over 0, which means it's 1 times infinity, is infinity. Now, we're going to infinity, yes, but we're going to the wrong infinity. Remember, which side are we approaching 0 from? The left. So what sign are the numbers from the left? Negative. So the denominator will be negative. So we're approaching negative infinity. If we were approaching 0 from the right, after L'Hopital's rule, we would get 1 over 0, but it would be a positive infinity because we're coming from it from the right. You have to be very careful on which side, if you do one-sided limits, you have to be very careful on what sides you're approaching it from. Okay, so those examples were all 0 over zeros. We'll go to the other end of the universe and go to infinity over infinity. We have limit of secant x over 1 plus tangent x. The point of contention is pi over 2. Why? Okay, remember from chapter 2. Why are we picking pi over 2 as our limit point? In this function, what happens at pi over 2? What is secant at pi over 2? Secant is what? Cosine at pi over 2 is 0. So the numerator goes to infinity. Tangent at pi over 2 is sine over cosine at pi over 2. Sine at pi over 2 is 1, cosine is 0. So this function goes to, so we have 0 or infinity over infinity. That means it doesn't exist yet. If it's infinity over infinity, it's an indeterminate function. So how do we fix that? L'Hopital's rule. The first examples we looked at was 0 over 0. Now we're looking at infinity over infinity. Okay, now, unless you have them written down someplace, what are the derivatives of secant and tangent? Secant x is 1 over cosine. So the derivative of 1 over cosine we use quotient rule. Cosine times 0 minus 1 times sine, that's sine x, over cosine squared x. So negative sine x over cosine squared x is the same thing as negative. Cosine is negative sine, so it's positive. Yeah. So we have sine over cosine times 1 over cosine. Sorry. Derivative of cosine is negative sine, so the two negatives cancel, so it's positive. So we have tangent secant, or secant x tangent x. The derivative of 1 is 0. The derivative of tangent is over cosine. So we take the derivative of that. Derivative of sine is cosine is negative sine. So we have cosine squared minus negative, so it's plus sine squared all over cosine squared. Cosine squared plus sine squared is 1. 1 over cosine secant, so it's secant squared. So we got the first derivatives. Again, if you don't remember them, or you don't have them written down somewhere, you can always derive them yourself using the quotient rules. So what is secant at pi over 2? Infinity. Tangent's infinity, so we have infinity times infinity over infinity times infinity, so we're back to infinity over infinity. What do we do now? Actually, let's always check algebra. If we have secant times tangent, secant x, these cancel. We have tangent over secant. Sine over cosine divided by 1 over cosine. Take the top one, so it's sine over cosine times the flip of the bottom. So we're left with just sine x. So this thing becomes the limit as x approaches pi over 2 of sine x. Because everything, I mean, since they're all secant and tangents, which are all terms of cosine in the denominator, we can do something about it. Secant squared is secant times secant, so each one of those get a secant underneath them. So what is sine at pi over 2? So the limit is 1. The reason I try to look at an algebraic shortcut is because I didn't want to do that. That seemed like too much work. So let's see if there's a shortcut. Let's look at another one. Example 7. The limit as x approaches infinity of ln x over 2 radical x. Limit ln goes to infinity is infinity, infinity. So we have infinity over infinity. L'Hopital's rule. What's the derivative of ln x? 1 over x. dx, which is 1. The derivative of ln x, is square root of x. 1 over 2 square root of x. The 2's cancel. One over x divided by 1 over radical x. One over infinity is infinity, or 0, and that's 0, so we have 0 over 0 now. We can fix this algebraically. One over x times square root of x over 1. We have square root of x over x. What can we do now? But they're both, remember, at the top and bottom, they're both going to infinity. Square root of infinity is still infinity over infinity. So we take L'Hopital's rule again. Derivative of radical x is 1 over 2 radical x over 1, which is 1 over 2 radical x. As x goes to infinity, the bottom goes to infinity, so the answer is 0. As x goes to infinity. Let's do one with an e. The limit as x approaches infinity of e to the power x over x squared. So if we plug in infinity, e to the power infinity goes to infinity over infinity. So we could do L'Hopital's rule. The derivative of e to the power x is e to the power x. Derivative of x squared is 2x. They still go to infinity over infinity. So L'Hopital's rule again. The derivative of e to the power x is e to the power x. Derivative of 2x is 2. As x goes to infinity, we have infinity over 2 equals infinity. Example 9. Limit as x approaches infinity of x times sine 1 over x. This is an example of infinity times 0. As x goes to infinity, this goes to infinity, 1 over infinity goes to 0, sine of 0 is 0, so it's infinity times 0. I'm not trying to make you work this one out by yourself, because this one is a little bit more complex. Because of this 1 over x in the trig function. Let's define h as 1 over x. So our equation now becomes, as h goes to infinity, because we now switch it from x to h. So h, x itself would be 1 over h sine h. H approaches infinity, we have sine h over h. That's the same as sine x over x, which becomes what? The alternate way of doing this, you'd have to do a product rule, and then you have the sine u, which would grow pretty quick. We have to have sine u du, and do the fishy thing again, so it's a product rule. So this is whenever you have a trig function with a rational angle, substitute another variable in it for that rational function. All right, let's see what else we got here. Let's look at infinities minus infinities. Example 10. Limit as x approaches 0 of 1 over sine x minus 1 over x. The easiest thing to do here, what approach would you take? Were you going to split them up? You can either split them up at two different limit functions, or you can combine them, have one limit function. In other words, you could do it limit as x approaches 0 of 1 over sine x minus limit x approaches 0 of 1 over x. Or, which would I suggest, limit as x approaches 0 x minus sine x over x sine x. Get a common denominator, and this one needs an x, this one needs a sine x. Get a common denominator, and now work it through. Because what have you just done when you do this? We've now converted it from infinity minus infinity to 0 over 0. This way, we'll just have longer, more drawn out derivatives. So take L'Hopital's rule, since we have 0 over 0, as x approaches 0, derivative of x is 1, derivative of sine is cosine. One cosine. So it's sine x plus x cosine x. Is that still 0 over 0? 1 minus 1. 0 plus 0. So it's still 0, 0. So we do L'Hopital's rule again. That's 0. Derivative of cosine is negative sine, so that's a positive sine. Derivative of sine x is cosine. X cosine, which is 1 negative sine. That's cosine x sine x. 2 cosine x minus x sine x. Cosine plus cosine is 2 cosine minus sine x. When we put 0 in there, sine of 0 is 0. 2 times 1 minus 0. So it's 0 over 2, which is 0. What I did was, when I did this, when you do these product rules, are these derivatives on top, this is no longer a quotient rule, this is now a product rule here. X cosine becomes cosine plus x sine, or minus cosine x. Okay, so those are the examples of the functions themselves being indeterminate. The exponents could be indeterminates also. That's where the radical functions come in. A to the power m n over m is the same thing as the nth root of a to the radical a power n. So you can have 1 to the infinity power, you can have infinity to the infinity power, you can have 0 to the infinity power. This is 1 to the 0 power. 1. What is infinity to the 0 power? Also 1. So the question is, what is 0 to the 0 power? I don't know. That's indeterminate. That's what makes it indeterminate. That's why we don't deal with the ones and infinities at power 0, because those are automatically 1. But what if 0? So, if the limit as x approaches some non-zero, well, some real number a, so if we take the ln of a function, the limit of the ln of that function equals L. Then, limit as x approaches a of f of x equals ln, or the limit of e to the power ln f of x as x approaches a. Since the ln f of x of the limit becomes L, we have e to the limit as x approaches a, or x equals a. This is a very important if. Limit the natural log of a function. Why do we use natural logs? Because we can have exponents also, the e's. Example 11. Show that the limit as x approaches 0 from the right of 1 plus x to the power 1 over x equals e. So we have to now use what we just defined up on top first. So what is f of x? F of x is the base. 1 plus x. Get the whole function. Because the whole function has to be examined. So the f of x in our function up there, the f of x is that. So we're going to follow the same logic here. So if that's true, then ln of f of x becomes ln of 1 plus x to the power 1 over x in rules of logarithms. If you have an exponent, that comes out in front, plus x. Then we take the L'Hopital's rule. Of the limit as x approaches 0 from the right. Okay, does everybody understand why we're taking the L'Hopital's rule here of the limit? Because as x goes to 0, this becomes 1. 1 over 0 is infinity. So it's to a indeterminate exponent. So this becomes the limit of ln f of x is the limit as x approaches 0 from the right of our function here, ln 1 plus x over x. This was defined up here. So that's what we're taking the limit of. Oh, using L'Hopital's rule, what do we get? Limit as x approaches 0 from the right. The derivative of ln 1 plus x. What's the derivative of ln? One over x. So it's 1 over 1 plus x. The derivative of x is 1. We have the limit as x approaches 0 from the right of 1 over 1 plus x. When x goes to 0, we get 1 over 1, which is 1. Not done yet. What were we supposed to find? We're supposed to prove that it's e. That's e. How do we do that? So the limit as x approaches 0 from the right of our original function is equal to the limit as x approaches 0 from the right of f of x, which means now we can take ln of that, limit as x approaches 0, e of the ln of f of x, ln of f of x is all of this. That's what ln x, it equals 1. So e to the power 1 is e. A little confusing. What we have to do first. The first thing we have to do, we have our function, take the ln of it. And then work to simplify it out. Because then we can take the limit of that ln function. That gives us the limit value. Now, this part here is saying, where did all this come from? It came from here. if the limit of ln function of L is L, then the limit of f of x is equal to the limit of e to the power ln f of x, which is e to the limit. This is the limit. So it's e to the power 1. So we're using this rule in here. Any questions? So the question should be, why do we take an ln? Well, we're taking ln because our exponent has a variable. We have to get the variable out of the exponent. That's what the ln does, because of this rule. Ln x to the power n is n ln x. If you have an exponent, if your exponent has a variable in it, you have to get it down. The only way we can do that is by the ln. So that's why we take the ln of our function, bring down the exponent. Now we can take the limit of it, since we now have no exponential equations. Take the limit of it, find the limit, which is that, plug it back in the original equation because of this rule. Yes. Because ln is the inverse of e. What happens here is the e and the ln cancel out, and we're left with the limit of the function, which is 1. So yeah, that's the reason, because if we took log, what base would it be? If it's log base 10, we have to raise it up 10 to the log base 10 of the function. E is just easier to work with. All right. That does it for that section.